Good morning to all of you. So, today we will start a discussion on a case study on microcanonical ensemble. So, in the last class we looked at what is meant by a microcanonical ensemble. So, this is the ensemble of fixed n, v and e, and these are systems which are thermally and mechanically isolated. Thermally means you have the energy constant, and mechanically means you have the volume constant. And I would like to discuss a few case studies of microcanonical ensemble. So, I will take two case studies. Okay. So, one case study would be the study of discrete degrees of freedom. So, I will take an example from the world of discrete degrees of freedom. And examples here would be particles with energy levels. So, I will take the simplest case of a 2 level system, where the particles in the system can exist only in one of the two levels. Okay. For the case of continuous degrees of freedom, and we shall visit this case study in the next lecture, I will take the example of an ideal gas. Now, we say that the ideal gas has continuous degrees of freedom because the particles in an ideal gas can take any value of energy from 0 to infinity. So, we consider this as a system with continuous degrees of freedom. Okay, the momentum degrees of freedom are continuous, whereas in the discrete degrees of freedom case, the particles can take energies only in these two levels that we are going to talk about. So, today we will discuss the case of the discrete degree of freedom or the 2 level system in microcanonical ensemble. Okay. So, we will take the case of a 2 level system in the microcanonical ensemble. Now, this means that we take n particles in 2 levels. Okay. So, the 2 levels mean that we take 2 energy levels with values 0 and epsilon. These are the 2 energy levels, and you can put particles in these, you can distribute these n particles like this, some of them being in the excited state, some of them being in the let us say the ground state. Okay. And naturally we can call the occupation number or the excitation, I would say the excitation state. Okay. So, the excitation number, the excitation can be taken as either 0, basically mean it stays in the ground state, that the ith particle is in the ground state. We can take the excitation of the ith particle as 1, that only means that this is in the excited state. Okay. So, this way if I compute the total energy, which will come out to be summation over all particles, the state in which the particles are, okay, and the energy level. Okay. So, since I have taken the energy levels as 0 and epsilon, the total energy is summation over all particles, the excitation state times epsilon. So, this will, suppose your first particle is in excited state, you take Ni as 1, the next particle is in ground state and the next is also in ground state, and so on and so forth. You will have ones and zeros, and in the end what you will have is basically the sum as some n1 times epsilon, where n1 is clearly the number of ones that you had. Okay. So, you can write down the energy as total energy as n1 times epsilon, where n1 is the number of excited particles. Okay. Only for 2 level systems. So, if you had 3 level systems, you would have you have to take a 0 epsilon and probably epsilon 1 or something. So, in that case your energy levels will have one more energy state. So, now we can think of the probability of finding the system in a certain microstate mu. Now, microstate mu here is a certain combination of these excitation values. So, you say that the set of Ni's, so if I take N0 as 2 and you take N1 as 1, then basically this is a microstate for a 3 particle system. Okay. So, the particular set of Ni's that you take constitutes a microstate. Okay. So, you can take for n equal to, let us say 10 particles, you can take the ground state number of particles in the ground state. Okay. So, as simply I am going to take this as let us say I am going to take N1 as let us say 6 and n minus n1 in the excited state as 4. So, this is basically a particular microstate. Okay. So, you can change these microstates and obtain the values of the system at you can construct system in different microstates, and I am going to write down the this probability of finding a system in a particular microstate, okay, as just 1 upon the total number of states accessible to the system, okay, because each microstate is equiprobable. Okay. And in this way I can write down the microstate as a function of total number of particles and the energy E. Okay. So, inside this energy E is the information of number of particles in the excited state. So, n is the total number of particles, n1 is the excited particles. So, n and n1 together constitute the total number of microstates in the system. Okay. So, then what we have is basically right. So, this is the probability of a particular microstate corresponding to a macrostate N1 or n comma e. So, n comma e specifies a macrostate which has basically omega of n comma e microstates. So, the above expression says that if you have these many microstates for a macrostate n comma e, then the probability of finding a system in one of the microstate is essentially 1 upon omega, because these microstates are equiprobable. Okay. Fine. So, if there are 10 microstates, then the probability of each microstates is 1 by 10. Is it okay? Right. So, then we can compute this will be clear. So, you compute the total number of microstates for this particular macro state. Okay. So, we have basically this is a macro state. Okay. And omega, which is the number of microstates, is nothing but the number of ways in which you can arrange n1 particles in the excited state. Okay. So, these many basically these many microstates exist in this one macro state of n comma e. Okay. Now, we assume that these n1 and n minus n1, they are all very large. Let us say that our n particle system has large number of particles and hence large number of particles in the excited state. So, these values of number of particles in both excited state and ground state as well as the total number of particles are very large. So, under that assumption I can approximate these numbers using Stirling approximation. I can use the Stirling approximation and write down our n factorial as n by e to the power n factorial n to the power n, and n1 factorial as I am going to use the approximation symbol here because these are approximations, as n1 by e to the power n1, and finally I can write down n minus 1 whole factorial as n minus n1 divided by e to the power n minus n1. These are Stirling approximations. Of course, I have dropped terms which are quadratic in which are I have dropped terms at the prefactors of the order 2 pi n, but that is not necessary here. So, if you use these Stirling approximations in your equation, let us label this as equation 1, we can write down our omega number of microstates in this macro state n comma e as n to the power n upon n1 to the power n1 into n minus n1 to the power n minus n1. Okay. The exponents will cancel, and now I can take logarithms on both sides. Okay. And noting that the entropy is related to logarithm of omega by the Boltzmann's expression. So, I can write down my entropy S over Kb as n log n. This is a logarithm to the base e natural log minus n1 log n1 minus n minus n1 ln n minus n1. Okay. Is that fine? Let us call this as equation 2. Now, we know from previous lectures that the value of thermodynamic temperature, okay, is nothing but the derivative of entropy as a function of energy. Okay, so we know that the temperature is given by this thermodynamic expression. Okay, in this case we have the constant number of particles as the extensive variable. So, I am going to take the derivative of equation 2 and get temperature. So, I am going to write down my 1 upon temperature as simply Kb times, and just for this reason, for the time being, note that I can convert this derivative to a derivative on n1 by simply taking an epsilon outside since you by noting that the total energy is a variable of purely n1. Okay. So, I can write down this derivative in terms of just n1. So, that gives me this derivative as so, I can write this as Kb upon epsilon and the first term is a constant because it is totally a function of n and n is a constant. So, the second term will give me minus 1 minus ln n1, okay. Then I will get plus 1, that is the derivative of ln n minus n1, and finally I will get plus ln n minus n1. Okay. So, now you can knock off this one and that one and write down your temperature as Kb over epsilon into logarithm of n minus n1 upon n1. Now, this is a beautiful relationship which tells you something very important. You see, in this expression I know that ln of any quantity is greater than 0 if x is greater than 1. The moment x becomes less than 1, logarithm becomes negative. So, for this logarithm to stay positive, I must demand that n minus n1 upon n1 should be greater than 1 for t to be positive. For the logarithm to be positive and hence temperature to be positive, uh, we must demand that n minus n1 upon n1 should be greater than 1. So, this basically tells you that your n1 should be always less than n by 2, because if you put n1 as n by 2, n minus n1 by n1 becomes 1, exactly 1. Okay. And the moment your n1 becomes larger than n by 2, the numerator becomes smaller than n by 2, denominator is already larger than n by 2. So, n minus n1 by n1 will become smaller than 1. Okay. So, I will say that n should remain less than n by 2 for temperature to be positive, right. So, if you simply say that if n1 exceeds n by 2, what happens? N minus n1 will be less than n by 2, because the total is n. The denominator n1 is already greater than n by 2. So, I can write that n minus n1 by combining these two, I can say that n minus n1 by n1 has become smaller than 1, and hence logarithm of n minus n1 by n1 has turned negative, thereby turning my left hand side negative, which is 1 over temperature. So, it implies that 1 upon T has become negative, which implies that my temperature has become negative. What is going on? So, I will tell you what is going on in a short while, but this expression gives us the conclusion. Let us proceed by making this not conclusion, let us proceed by making this observation that our maximum number of particles is n by 2 in the excited state, and this means that our T turns out to be negative if excitation or number of particles in the excited level is greater than half the number of total particles. Okay. So, this is the observation that we have made here. Okay. So, that is the observation we made here, and I am going to proceed with the discussion by saying that the maximum excitation or population in the excited state appears to be half filled. So, in a two level system, by raising the temperature of the system, you can only increase the number of particles in the excited state to be half the total number of atoms. That is the maximum you can do, and we can see that by inverting this expression. Okay. So, I will invert this expression for energy and show that the maximum you can do is just a half filled in the excited state. Okay. So, let me pull this expression here. Okay. So, I am going to explain this this maximum excitation to be half filled and not more than that in two ways. Okay. So, I will explain this using so the question is why is the N1 max equal to n by 2 in these two level systems. So, this question will be answered using two arguments. So, I will use one argument which I will say as the energy argument, which is perhaps easier to understand at this moment or immediately understandable, and the other argument that I am going to use is basically the argument of disorder or entropy argument. Entropy is a measure of disorder. Okay. So, it is a delightful scenario to basically understand why I can't increase the population in the excited state by more than half using two different methods, by the argument of energy and by the argument of entropy. So, let us use the energy argument, which is straightforwardly obtained from the last expression on the temperature. So, if I invert this expression for energy, what can I do is basically I can say that my from the, let us call this as some equation third, fourth, let us call it as third. So, I can say from equation 3 I can write down the value epsilon upon kBT as just the logarithm of n minus n1 upon n1, which means I can say n minus n1 over n1 is e raised to epsilon upon kBT, and I can simply say this is n by n1 equals to 1 plus e raised to epsilon upon kBT, and finally I am going to write it as n1 equals to n upon 1 plus e raised to epsilon upon kBT. Okay. Just simple transposing terms on both sides. Now, I will multiply epsilon on both sides, which is nothing but the expression for energy, because epsilon into n1 is my energy. Okay. So, let us write it as okay. So, this is basically my energy. So, the energy is epsilon n upon 1 plus e to the power epsilon over kT. Now, let us plot this. We learn a lot from sketches. Okay. So, let us sketch it. So, I am going to sketch my energy versus temperature. Okay. Now, as you can see at t equals to 0, the denominator becomes e raised to infinity plus 1, which is infinity, and 1 upon infinity is 0. So, my energy is 0, and at t goes to infinity I have e to the power 1 by infinity, which is 0, which is e raised to 0, which is 1. So, I have the maximum energy as n by 2 into epsilon. So, let me construct this maximum value of energy. So, my energy as a function of temperature will monotonically rise, and its maximum value is supposed to be just n by 2 epsilon. And as you can see that I can go to, this is called the entire region below this dashed line is called as the region of positive temperature. okay. And I know that if I try to push a number of particles more than half to the excited state, it goes to the region of negative temperature. So, I am going to call this region as the region of negative temperature. Now, you can see why negative temperatures are hotter than the infinite temperatures. So, if I start from a system which has less number of particles in the ground state, I continue increasing the temperature of the system, I can go to infinite temperatures, yet I will not be able to push the number of particles more than half to the excited state. On the other hand, if I somehow start with a system which has more particles in the excited state than the ground state, then the system is already in the negative temperature state. So, I will say that the negative temperature state is hotter than the infinite temperature case, because even with infinite temperature I could not excite more than half of the number of particles, but somebody has given me more than half, which means he has given me a hotter system, but I know his system is in the infinite temperature state. So, it apparently is hotter than t equals to infinity, because I have put more particles in the excited state. Okay. So, this is the reason why if you start with a positive temperature, you cannot go to more than half filled, precisely because the amount of the highest possible temperatures you can reach in your system is by will only take the excitation to 50% in your system, and so that is the reason why you can't go to negative temperatures by simply heating the system. The other argument that you can give is the entropy argument. So, this argument means that our S behaves like logarithm of omega, okay, and this is a monotonic function in the sense that if omega monotonically increases, then my entropy will also monotonically increase with omega. Now, I know that my omega is basically the number of microstates, and that is n factorial upon n1 factorial into n minus n1 factorial. This has a maximum at half filled excitation. Okay. So, the binomial multiplicity peaks at the value n by 2. Okay, this result, that the maximum value of NC R is at NC n by 2. So, this has a maximum of n by 2, which means my omega max is sitting at so I can expect my entropy which is a monotonic function of ln omega is also sitting at n by 2, because entropy is a monotonic function of omega. So, which means I can plot the I am going to use a bigger figure here, because this is a beautiful argument. The disorder argument. So, I am going to plot this as a function of E, and noting that E is nothing but purely a function of n1. Okay. I am going to plot S versus E. I know at n1 equals to 0 and hence E equal to 0, my entropy should be 0, because when n1 is 0 or our energy is 0, okay, omega is nothing but n factorial by n1 factorial into n minus n1 factorial. At n1 equal to 0, omega at n1 equals to 0 is nothing but 1, because it simply becomes n factorial upon n factorial. And what is ln of 1? 0. Therefore, our S becomes 0. So, I have a point here, okay. And the maximum number of n1 I can have, okay, is basically n. So, I will say this is the minimum, okay. The scenario where excitation is maximum is that all of them are excited. Again here I can say that omega as a function of n1 is nothing but n factorial upon n1 factorial into n minus n1 factorial. Now, if you put n1 as n, this is nothing but 1 again, because now you have n factorial upon n factorial again, which means my entropy, which is logarithm of omega, is again 0. So, this was the case of maximum, this was the case of minimum n1. Okay. So, I will basically to be symmetric in my, so I am going to write it as simply means n equals to E equals to, this is the case of maximum. So, basically I am again back to 0 when my energy is n times epsilon, and I am 0 here, and somewhere at the peak at the value when n1 becomes n by 2, the energy is basically n by 2 epsilon, I have a peak. So, I am going to draw a function which has a maximum . So, this is the maximum value of entropy. And as you can see from thermodynamics, the slope is basically 1 upon T, because it is ds over d, this is the slope, okay, ds over d, and you can see as you increase your energy your slope reduces. So, this is the direction in which slope reduces, which means your T increases. So, 1 by T reduces, which means T increases. Finally, when you reach this peak, the slope 1 by T is 0, which means this is the regime of infinite temperature. So, when you reach in the energy here, you would have reached in the entropy picture here, when the slope becomes 0 or temperature becomes infinity. Now, if you try to go on the other side, the slope 1 by T has turned negative. So, what you are trying to do is basically in this side. So, I will say that my T increases or S increases, my disorder also increase, but on this side I will see that my disorder decreases. Okay. So, what is happening is that above the maxima, if I try to put in more energy, my system becomes more and more disordered. So, if I try to increase energy from 0 to n by 2 epsilon, the system gets more and more disordered all the way up to infinite temperature, which is the point here at the maxima. You cannot cross this. Now, the moment you try to cross it by artificially pumping particles in the excited state more than half filled, you go to the other side of the curve where your entropy begins to decrease. So, this is like I am putting more energy. So, this would be the region where you know, so I will say that S decreases with energy and here S increases with energy. And this is not possible. I mean, you cannot, this is a weird scenario that you are trying to increase energy in a system and create it more ordered. It would be like asking a bunch of students who are more hyperactive, you know, and expecting them to be more ordered. Hyperactivity means they have more energy, they will be constantly jumping up and down, but apparently this group of students who are hyperactive are more ordered than this group of students which are normal and you know, not hyperactive, they are more disordered. So, this is the entropy argument that you cannot exceed the number of particles in the excited state more than n by 2. So, the only way to exceed, you know, beyond n by 2 is to start with the system with n1 greater than n by 2, which means you have already started with a negative temperature state. And as soon as the system, you know, comes in contact with a reservoir at positive temperature, with a reservoir, you know, at some positive temperature, let us say Tr is greater than 0, there will be in exchange of energy between these two systems. In fact, this system would only lose energy, any excess energy that it has, it will lose that energy to the reservoir and come back to a positive temperature, and thereby, you know, after this it will come back. So, eventually you can say that this 2 level system returns to a positive temperature. So, you can start with more particles in the excited state than the ground state, but this would be a metastable state. This would not be a system that will stay in negative temperature forever. So, as soon as the system comes into contact with the reservoir at finite temperature, it will come down to positive, it will come down to a lower energy such that its temperature turns positive. And this is the manifestation of negative temperature states. You can think of the negative temperature state to be an exceptional state where putting more energy yields more order into the system, thereby making the slope ds by d negative. So, in the next class we will proceed with the system with continuous degree of freedom and discuss the case of ideal gas in the context of microcanonical ensemble. So, we break here and we meet in the next class.